I want to look at one potential place that a logistic function could come in handy in modeling climate change, right? The kind of this real world application. And yeah, there's a lot of different measurements that are currently growing at exponential rates. And one of them is the CO2 concentration in our atmosphere. And so this is kind of the data that's taken from Mauna Loa, a measurement location in Hawaii. Here's the actual data that they're measuring in that location, and this is like ice core data that you can kind of read about what that means. But there's kind of a baseline of about 278 is around like where we had been for a really long time. If you kind of look at this is like 10,000 years, like we're pretty flat, maybe a little bit higher than 278, but like in this range, we're pretty flat for a while, and then we start to kind of take off. Exponential growth here. It can't last forever, right? Like just theoretically considering, there's got to be some kind of max at some point because there's only so much carbon that the world has kind of stored underground. So there's got to be some point where it caps off, whether that's when we exhaust all of the carbon reserves that are buried underground, or whether that's like us kind of taking some action to mitigate this, right? But we have this exponential growth at the beginning, and eventually it's going to taper off at some point in time. So I took this, and they have the actual data from someplace. But one thing, like if you didn't find data, I did this actually a few months ago. But I just kind of overlaid it along this, so I could kind of get some data points to kind of create my my model. So I used 0 just being 2000, saying, right, like this is the turn of the millennia. My X value of 0 corresponds there, where we were at about 370 parts per million of CO2 concentration in 2020. We're at 415. The latest measurement that you saw on the last website was 417. And I just picked a few other data points back here, right? Where were we at, right? Say 1980 and 1960, and right, all of these other points in the past. Every single tick mark here is 10 years. And so I just kind of created this. And then I put it up into Desmos, right? Said here we go. 0 corresponds to 2000. This is 20 years before 2000, 20 years after. And here's my model that looks like kind of exponential growth at the start here. In your logistic project, I asked you to kind of try to take 2 of these points to make your equation. I let Desmos do some of the heavy lifting here for me, where I used I used x1 and y1 in my table. And then this little tilde, right, that little tilde symbol will kind of force Desmos to run a regression to fit this to the best possible data it can. These fudge factors are saying, right, like I'm not at 0, right? Like the baseline for the parts per million concentration isn't at 0. So I needed to shift that up to kind of the like where the baseline was at 278. And so I did that, and then I could have just made this be C, right? Like, but I wanted it to have some meaning. So in this case, my C is the actual, like, what's the ceiling parts per million there, right? So I could have shifted everything down and then reshifted it back up. But this C here is my, like, what's the cap? What's the parts per million cap that we're eventually going to reach? I could have Desmos do that for me, right? I could use A, B, and C, and Desmos would fit this to the best that it possibly could. But if I do that, Desmos thinks that we're growing too fast for it to actually be truly logistic. So it puts in a C value that kind of creates this asymptote saying we're going to go off to infinity at the current rate in about 2090 or so. I know that's not the case, so I put in like, hey, let's put in a C of about maybe 500 and let this go between 420, where we're currently at, right, 415. So we, it can't be less than that, to, I don't know, maybe 2000. And so I made it the C value. Right, I can kind of change it to best fit the data. Right, this R squared here term. That's a measure of like how well it's fitting here. right? So the higher I go, the better the R squared, the better it tells me, hey, the model is fitting this pretty well, the higher up we go. But yeah, this would kind of depend on, right, where are we trying to cap off. If you look here, they give a few different, like, the future scenarios. You can dig into this a lot. There's a whole bunch of work that's being done. These representative concentration pathways are a bunch of different models that they've done to try to model this already. The 8.5, this is like if we don't do anything, right? If we don't do any mitigation, we just keep accelerating our use with increasing population densities and everything like that. And then there's a few different like targets, right? Some target pathways for what this would do. So this is the RCP, representative concentration pathway 8.5 would, right? This thing is just kind of, it goes, right? It keeps on increasing and increasing and getting higher and higher. And you can see, right, this has it going up past 1200 and parts per million, and increasing beyond that, right? You could pick some different ones, right? This one, I don't know what's going on here with that little, like, hey, we're just going to cut it off and then slowly ramp it back up, but it doesn't seem very realistic to me. But even if we did cut it totally off here, right, this is still going to be increasing for a while before it levels off. So, right, this, I'm saying, hey, I could kind of pick, right, 420, that doesn't seem to fit the data very well, right? We're not going to level off there. So maybe we're going to level off somewhere out here, right? Maybe 800 parts per million or so. And this would build my model, right? I did this. The Y1 is approximately, use the X1. Here's my logistic function for that. Gives me different A and B values. If you want to do that for your project, instead of finding the two, and you want to focus a little bit more on like the actual research, that's where you're going to concentrate your efforts, that is totally okay. Finding the equation through 2 points is good mathematical practice. If you're going on to AP Calc next year, I highly recommend doing that practice just with the algebraic manipulation of how you would get to those A and B values. You can't do it with, right, for that you'd have to pick a C, right? Just like kind of I'm doing here, I'm saying C 800 parts per million is my cap. In this one too, right, like this is the Australia COVID data, just jumping back there quickly a second. I could have put in a C that it would give me, right? Like what's the best fitting data here? I didn't for that because the tail end of this actually isn't behaving very logistically. It's kind of still increasing a little bit more linearly. But yeah, so I just picked a C. If you're going to find it through 2 points, you need to specify what is that C value. Desmos will give it its best guess. If you just put it in there, it'll say like, hey, for this, the highest possible R squared value, which is like the least possible error, the C value is this, right? So through 2 points, specify. You decide what is the highest point. Desmos otherwise can do the lifting for you there. But yeah, so this is just one option for how to do this. You could have, again, picked a couple of points and found the equation of best fit through there, not the equation of best fit, but like the equation that went through those 2 points. Yeah. I did a little bit of other stuff just through, right, like the exponential, what if we just continued on purely exponentially, what would keep going on, but hopefully we're going to peak off at some point in time. And then this other graph down here, I kind of use this green one as my temperature, right? So saying what is, right, there's always a correlation between carbon dioxide and temperature, right? Carbon dioxide is a greenhouse gas. It reflects things back, and you can kind of look at a bunch of different research about that. But the more carbon dioxide there is in the atmosphere, the more the heat that's leaving the Earth gets reflected back to it, because carbon dioxide absorbs energy in that infrared spectrum of that we think of as heat, and then re-emits it in that same spectrum. Some of it back out to space, but some of it back to Earth. So it kind of acts as that blanket, right? And so there's, right, what the specific relationship is, right? There's a little bit of room for error here. So I kind of put in this is my temperature, saying like there's going to be some sort of direct relationship between carbon dioxide concentrations and what the temperature is. This would be like, right, for every 100 parts per million, we increase by 1 degree, right? This would be for every 200 parts per million, we increase by 1 degree. If you kind of look in here, you can kind of do a little, right, between here and here is about an increase of 70 parts per million and an increase of about like 7/10 of a degree. So it seems to be about like, 1 to 100. But if you wanted to be a little on the safe side, you could say it's maybe 1 to 200. And then this function would model like what the temperature is. So, right, if it's at 200 parts per million to increase 1 degree, then in 2008 we should have seen about a 0.54 degree anomaly, like above the baseline, above the zero. In 2008 is actually about, right, pretty close to that, right? It gets up between like 0.6 and 0.4. So you can kind of play around with that a little bit, but then you could use that to predict, right? Like, hey, if this is my model, right, and we're going to cap out at 800, where are we going to be at in the year 2100? And this is saying, with this model, with that 800 parts per million being the cap that we are approaching, in 2100 we'd be about 1.7 degrees Celsius above the average. So just different things to kind of play around with, to kind of look at. And yeah. So again, have fun with this project. If you want to do something related to climate, go for it. If you want to do something just totally different and silly, right, a zombie apocalypse and the virus spreading, right, it is your baby. Do with it what you want. Have fun.